Because you have to consider the hidden variable being one value versus other value and sum both. You have to marginalize it. Anytime you have to do marginalization, it involves summation or integration. And you know who hates sums? I know you probably like sums. You hate multiplications. Who hates sums? Who hates sums? Logarithms. Logarithms hate sums. They love multiplications. You see what I'm saying? It's the multiplication that becomes sum after the logarithm. If it is sum, I don't know what they have to do with the log and that. That's actually why EM comes. That's actually the way to understand how EM comes. But until you get to a point where you don't have complete data, that means you have incomplete data, you have a simple scenario where known topology of the Bayes network and the attributes of the data are known. In which case, it turns out that irrespective of how crazy the network is, this one is not particularly crazy. However crazy the network is, you can be sure that all the partial derivatives lead to unentangled equations. Which means dou L by dou theta just basically will be in terms of theta. So you equate to 0, you get the value of theta. And the dou L by dou theta 1 will be just in terms of theta 1. So you equate to 0, you get the theta 1 value. What's the best way of solving simultaneous equations? The one, x plus y plus z plus etc. equal to something? The best kind of simultaneous equations have three simultaneous equations on x, y, and z. 2x equal to 4, that's one equation. Y equal to 3, that's the second equation. Z equal to, 2z equal to 5, that's the third equation. Now I solved simultaneous equations. But those are the good simultaneous equations. That's what you will get when you have Bayes networks with complete data and tabular CPTs. Tabular CPTs means CPTs like tables, which is the only things you do get in this class. In that case, all these equations will be easy to solve. So let me show you this. So essentially, if you had actually written the log version of this, right, you would have gotten this, right? C log theta plus L log 1 minus theta plus RC log theta 1 plus GC log 1 minus theta 1 plus RL log theta 2 plus GL log 1 minus theta. Huge expression where it just sums. And notice that each piece only has one of the variables. Now, if I do basically this is L, I always take logarithm, the log likelihood. Partial derivatives. So what is dou of the partial derivative of this with respect to theta? With respect to theta, the derivative of this is 0, this is 0, this is 0, this is 0. Right? So the only ones which have derivatives will be our old guys. Equal to c by theta minus L by 1 minus theta. Equal to 0, you get theta equal to c by c plus L. Again, that's what you would have done. You'd say, why are you wasting my time? But now you know. Now you know this is the right thing to do. Okay? And similarly, for dou L by dou theta 1, it's only this stuff will remain, this will die, this will die. Right? Because logarithm, the partial derivatives of those two are zeros. So then, once again, for this guy, it will be RC by theta 1 plus minus GC by 1 minus theta 1. You put it to 0, you get theta 1 equal to RC by RC. See where I'm going with this? Now, if I had a slide, I would have shown you that let's go back to the basis. Burglary, earthquake, alarm, John calls, Mary calls. If I can do this, hey, I seem to have done everything. Right? And I would argue that that's the same thing as this kind of a guy. So if I actually set up, so basically the complete data case for this would be each episode, for each event, I need to know, okay, burglary occurred, earthquake didn't occur, alarm didn't occur, John called, Mary didn't call. That's one data point. You see what I'm saying? That's one data point. If I give you 1500 of these data points, then basically I'm doing the same thing as here. So then you can compute the PB by just looking at all the data points total and the fraction of them where B is true, and say that is the PB. And if you were to actually set up the likelihood expression, it will be ugly, because it's ugly enough. For this one, it will be bigger for the 4 one, but for the 5 variable one, but it will be exactly working this way. Okay? And similarly, for alarm, basically, I need to compute, what would I need to compute? What is the probability that alarm equal to true, given burglary true, earthquake true, burglary, earthquake, burglary true, earthquake true, burglary true, earthquake false, burglary false, earthquake true, burglary false, earthquake false. Right? So if I just need to compute this number, I look at all the samples, take the samples where both burglary and earthquake were true, put that number in the denominator. And among them, see how many of them had alarm true. Put that number in the numerator. You say, Mom, I did Bayes network learning. Moms are very easily interested. Right? This is complete Bayes network learning. And it's the best that will ever happen to your life, because the likelihood expression nicely becomes unentangled equations, unentangled linear equations, not even non-linear equations. Unentangled means they are not simultaneous at all. The more general cases, pretty much after this anything, it would be actual non-linear simultaneous equations. So rather than directly solve for the minimum, you do the gradient essay. If you're a probabilistic guy, you would say essay. The gradient essay. It's the same as gradient descent, right in the opposite direction. Right? So when we come back next class, to the little time I'll have, 2 points I will make actually. One is, in all these cases, right, I'm essentially telling you, if I give you that topology, computing these numbers is extremely easy. Right? The question is, if you have a classification problem, if you have some particular classification problem, where the class can be true or false, class is fraud, fraudulent transaction. True, false. You're trying to classify it. And you have a whole bunch of variables, input variables. That is customer wealth, country of origin, and blah, blah, blah. Lots and lots of different attributes. You could argue that these somehow are connected to the fraudulence of the credit card transaction. If I could give you the actual network, then you can say, Mom, I'm doing Bayes network computation by just taking ratios. on just these 5 variables B, E, A, J, and M, right? There are multiple different ways I can connect them. We already saw different ways. Imagine in the B, A, J, and M, all you care is whether or not Mary calls. Like everybody wants Mary to call. All you care is will Mary call her. Okay? But I'd have to come up with some kind of a network configuration. This network configuration requires you to understand how Los Angeles works. If it's a random credit card transaction or something, I don't know what connects to what. So what I'll do is rather than go with this network, I'll say, don't give me the topology. I'll make up one topology. For everybody, I'll make up this kind of a topology. So you want Mary calls? Okay, Mary calls, I'll put it here. And everybody else calls this Mary call. Suppose I just made this as my topology. I can do Bayes network parameters. Because if I could do that for this, I can do it for this. Right? If you assume that all attributes directly are connected to the classification variable, what is this called? This is MBC with the big lock. Naive-Bayes classifier. All Naive-Bayes classifier does is, in fact, in my slides, I have this Rita Hayworth picture. Rita Hayworth, I believe, is the one who is famous for saying that whatever you do for Christmas, Jean Harlow, sorry. This is Jean Harlow. Okay. Jean Harlow said, whatever you get me for Christmas, don't get me a book. I have a book. Okay, I don't know if you guys get the joke. But anyway, Naive-Bayes classifiers say, you don't need to give us a topology. We have a topology. You see what I'm saying? Knowing how this domain actually works, this topology should make your blood boil. Thinking, what bosoness is this? That M, B, and E, and G are all directly causing M. That's not the way the real world works. But how do you know how the real world works? You have to make up something. In which case, Naive-Bayes classifiers always assume all attributes directly are connected to the class. Then it just becomes a very simple subcase of complete data-based network parameter estimation problem. And it involves essentially, if you could do this, you can do this, because you just make this up and then you just count the number of, for this kind of a thing, I need what is the probability of M, what's the probability of B, what's the probability of E, and then what's the probability of M given any of those. Just give me a second. Right? And so, actually, in fact, huge mistake. Let me do this. That actually the specific configuration that we pick is this. First of all, I should put it here. M causes A, B, E, H. This is the configuration Naive-Bayes classifier system. That is, the class variable causes the symptoms. And if the class variable causes the symptoms, then symptoms are independent of each other given class. Which means the numbers you need are prior probability of the class and prior probability of the symptom given the class. Those can just be computed from the data. I'll walk you through some examples. Okay? That's what Naive-Bayes classifier is. And it's one of the, basically at one point of time in 2006, I was at a Google faculty summit, and people were asking Peter Narvey, this is 2006. So Google has this machine learning stuff. What is Google machine learning secret? Said Naive-Bayes classifier. You're at least 2006 level of learning. And you remember, there was Google in 2006. I was doing quite well, and that's what it was doing. It's making up a particular configuration where class causes all the variables. Is that because that's true? No. Much of research is looking for the last case under the light, because that's where the light is. You pick this because this is easier to compute. So you would have done this for this scenario too, and you realize how bad this is. So when you actually take a random problem and you do naive-Bayes classifier, you don't expect miracles. The second idea is to try and actually learn topologies, which looks like a great idea, but for the fact that you have to be careful. It turns out that if you consider a network N and another network which is N plus some more connections. Do you understand what I'm saying? N plus one more connection. You can convince yourself very easily that the data likelihood would be higher for the more densely connected network. So the degenerate case would be, everybody will say, yeah, topology is everything is connected to everything. That way you can't go wrong. But then if everything is connected to everything, you need too many parameters. Too many parameters is overfit. So then what you will say is look for topologies that also wind up minimizing the number of connections. Not just maximizing the likelihood of the data, but at the same time minimizing the number of connections. Just like in the neural network you said, not only minimize the loss, but look for something that doesn't give too high a weight for you. We'll consider those two next class. And I might also mention what happens when, for example, I give the data with some of the variables values missing, which is expectation maximization. Okay, I actually took a lot of your time.